Hey, pre-calc students, this is going to be a really quick lesson today with some more symmetry in it. And today we're going to apply the concepts of symmetry to even and odd functions. So as far as definitions go, I've defined for you up here what an even function is. A function is even if for every number x in its domain, the number negative x is also in the domain, such that f of negative x is equal to f of x. So we talked about that kind of symmetry yesterday, that if you can replace x with negative x and the equation remains the same, that's going to be symmetry about the y-axis. So if we go kind of with our classic example of y-axis symmetry, which I think of as being f of x equals x squared. From now on, if I give you something in function notation, I think it's probably best to replace it with y equals x squared, just because this is what we were more used to yesterday. If I have to replace y with negative y, it's probably easier to see in this fashion. So of course, if I replace x with negative x, we're going to wind up getting y equals x squared all over again. So we know that y equals x squared graphically is certainly something that exhibits y-axis symmetry. So now from now on, as long as it's a function, things that have y-axis symmetry, we can classify as being even functions. So what I want you to think about is what are some other even functions that you know? Make a quick list right here, and then I'll show you what my list looks like, and hopefully we have some in common. All right, others that I can think of is, what about y equals absolute value of x? Just that parent function that looks like a V shape, that certainly has y-axis symmetry, therefore making it even. If we had y equals not only x squared, but what about x to the fourth? Or what about x to the sixth? Or x to some even exponent, okay? As long as it's there solely, right? There's no other terms added or subtracted here. Those would all be examples of even functions as well. And just because I know it came up on the homework from homework 1, how about something like y equals cosine x? That's a little bit tougher for us to show algebraically that cosine of x and cosine of negative x are the same. Okay, we can do it, but we might have to wait till we do more in-depth trig later on in the year. But if you remember the function cosine x, here's what it looks like on the positive side of the x-axis. It would repeat that pattern on the negative side. So look how nicely that exhibits y-axis symmetry. Cosine x is a good example of an even function. All right, meanwhile, what do we have if it's an odd function? So it says a function is odd if for every number x in its domain, the number negative x is also in the domain, such that f of negative x is equal to negative f of x. So this one I think is a little bit tougher to interpret in terms of the notation, but essentially what we're saying is that xy and negative x, negative y are both included in the function. And when that's true, that xy and negative x, negative y are there, it's symmetry about the origin. And this is kind of an easy one to remember because it's O and O. If it has origin symmetry, it's an odd function. Okay, remember, it has to be a function to start. So let's go with maybe this example here. I like this one, f of x equals x cubed. It's kind of nice that if it has an odd power, it's an odd function, as long as there's not, again, anything being added or subtracted afterwards. Let's prove this using our symmetry test. So we've got y equals x cubed. You not only have to replace x with negative x, but you also have to replace y with negative y. Okay, so do that in this fashion where you have negative y equals negative x cubed. And what happens algebraically is that negative x to the third power, a negative x times negative x times negative x, produces negative x cubed, right? X times x times x is definitely x cubed, but the coefficient out front is negative because a negative times itself an odd number of times is still negative. Well, in this scenario, if you divide the negative 1 out to get y alone, you get y equals x cubed again. So through that algebra, I've shown that this has origin symmetry, which therefore makes it an odd function. okay? And we know that y equals x cubed, if you were to pick points and reflect them through the origin, we can exhibit that symmetry here. So if we do the same thing that we did up above, maybe you can list some other odd functions for me, and I'll get you started with kind of the easy ones, like y equals x to the 5th, x to the 7th, you know, things with odd exponents. Again, as long as there's nothing being added or subtracted to those, we can definitely assume that those functions are odd. Some other examples that you might be thinking about, if we're going to trig, sine x is a good example of an odd function. It has origin symmetry. And one other that's kind of a nice example is y equals 1 over x. We graphed this on the first day of our functions unit. It was part of the important functions. Y equals 1 over x is this graph right here. It's called a hyperbola. And you can see that the points on this graph have that origin symmetry. So that's kind of a nice one too. If you were to do the algebraic test, replace x with negative x and y with negative y, you'll confirm that yes, you get the same equation again. So that's the main thing we're adding on today, is now not only just testing for symmetry, but if I give you something in function notation like f of x here, being able to classify that as being an odd function or an even function. Since we're talking about functions, by the way, what tests do we get to leave out for today's practice? In order for something to be a function, it has to pass, of course, the vertical line test. So we're not looking at any x-axis symmetry today, which is kind of nice too, because that means I can reduce my testing that I have to do. We don't care about x-axis because x-axis means it's not a function at all. Well, the premise today is that everything's a function to start, but what we're going to do is we're going to figure out, is it an even function, is it an odd function, or is it neither of the two? Now, although this is in your packet on page 11 here, the examples that I want to do with you are not in your packet. So just grab a separate sheet of paper. I'm going to show you just quickly how we can determine in each of these scenarios whether these are even or odd functions. Okay. So once you're done copying this down, and of course hit pause if you need me to, let's go to number 1. I'm just going to change this into y equals right away so I can start testing some symmetry. The nice thing is that you're going to start recognizing, oh yeah, I know absolute value of x, and I know what x to the 5th is. So be smart about your testing. If you know that this has y-axis symmetry, which I hope you do, then test y-axis symmetry first. How do I do that? You're going to replace x with negative x. Now remember, absolute value of negative x, that's just the same thing as absolute value of x, right? I mean, if I put like a little negative 1 there, the absolute value of negative 1 is positive 1. And we don't typically write that on the outside. So since this matches the original, we know that this has y-axis symmetry. And if something has y-axis symmetry, the conclusion is it's an even function. Now you can't be even and odd at the same time. So if you find that something is an even function, you can stop there. You don't have to test odd. That's another perk of today's lesson. Because in yesterday's lesson, you had to test all 3. Sometimes a certain relationship has more than one type of symmetry. But in this example here, once I find that it's even, I'm good to go. All right, I'm pretty confident we know what's going on with g of x equals x to the 5th. But let me quickly change that into y equals x to the 5th. If I'm smart about the process, when I see an odd exponent, I'm probably going to test origin symmetry first, because origin and odd would go together. So how do I do that? Well, negate y and negate x at the same time to see what's going on here. All right, so we get negative y equals. Negative x to the 5th power is just negative x to the 5th, because a negative times itself an odd number of times, like I mentioned earlier, is negative. Divide out the negative 1 to get y equals x to the 5th. What have I just confirmed? I know that this has origin symmetry because of the test, and therefore my now conclusion is that this is odd. Okay, doesn't even make sense to test even. We're not going to be both even and odd at the same time. Okay, 2 more to try. Number 3. y equals 8x to the fourth minus 3x. All right, so number 3, I'm looking at this first term and I see a lot of even numbers, so maybe I'll test y-axis symmetry first. That seems maybe likely if we have some even exponents and even coefficients. All right, so if I replace x with negative x, let's see what happens. Okay, make sure you do that in both cases. So I know negative x to the fourth is the same thing as just x to the fourth. Okay, a negative x times itself even number of times is a positive number. Negative 3 times negative x is plus 3x. And if I look at this equation and I compare it to the original, they're not the same. So this does not have y-axis symmetry. So it's not an even function. If you test and you find that it's not even, you do have to go on and then test to see if it's odd. So let's do negative y equals, make sure you plug in negative x as well. So here's kind of the test for origin. Well, we already did this a second ago, didn't we? We replaced the negative x's in there and found that that equaled 8x to the fourth plus 3x. So you can use some of the work from above and just copy it down without much thinking. Then last step, divide out the negative 1 to get this, negative 8x to the fourth minus 3x. That definitely doesn't match the original. So it doesn't have origin symmetry. No big deal. I don't know why I necessarily associate that with the sad face. All that means is that this function has neither of those symmetries, which means it's neither even nor odd. Okay. It's not even, it's not odd. It's just a nice old function without symmetry. Okay. Last one. F of x equals x over 1 plus x squared. All right, so yeah, let's just do a quick y equals there to see what's going on. So here's the thing. In this case, what do we have? We have we have an even exponent of 4, we had an odd exponent of 1, and that turned out to be neither. I don't know if that will happen in this one. We have an odd exponent on top, an even exponent on the bottom. I don't know. We'll have to see what happens. All right, so in this one, let's try y-axis first. If I just replace the x's with negative x's. Like that. Okay, so I made those replacements. And what does this turn into? Well, nothing happens on the top. We just have negative x. The bottom, squaring a negative x, we know makes it positive x squared. Does this match the original? Not exactly. I mean, on the top, we had positive x there, right? So no y-axis symmetry. Let's see if it's an odd function, meaning it has origin symmetry. All right, so we get negative y equals, put the negative x in both those spots. All right, we already know what this side becomes. We know that that becomes negative x over 1 plus x squared. How do I get rid of the negative in front of this y? I usually divide it to both sides, right? But in this case, just because we have a fraction over there already, I'm going to multiply both sides by negative 1, and look what happens. When I multiply this by negative 1, this becomes positive x up here over 1 plus x squared. But Mr. All, shouldn't we multiply the top and bottom by negative 1? Well, not really. Negative 1 over negative 1 is then positive 1 you're multiplying by. So yeah, you can just multiply the top by negative 1. That becomes positive x, and this matches the original. So because that's true, this has origin symmetry, so your conclusion is that this is an odd function. And you can go from there. All right, we'll do a little bit more with even and odd next time I see you, but hopefully this is not too much of a stretch after our initial day of symmetry. Let me know if you have any questions.